Hello, everyone. Thank you for joining us today. We are very delighted to participate in the Bridging Transportation Research Conference. My name is Sarah Masood. I'm an assistant professor of industrial and systems engineering at Wayne State University. And today I'm delighted to present our work on car following behavior of human drivers. This is a collaboration between University of Michigan and Wayne State University. And without any further ado, I'm going to start the presentation. We are all somehow familiar with autonomous vehicles. In the past few years, we have been witness to an increase in autonomous vehicle development and testing, with many mobility-oriented companies as well as original equipment manufacturers attempting to either open autonomous vehicle divisions or partner or acquire startups that focus on software or hardware development for autonomous vehicles. In short, autonomous vehicles are vehicles that rely on many sensors in order to sense their environment and self-drive to some degrees. In terms of different levels of autonomous vehicles, we have autonomous vehicle level 1, which heavily rely on driver assistance in order to for the vehicle to drive. And the maximum level of autonomy is level 5, where it has full automation, and without any drivers, the car can drive itself. As a result of the improvement of and enhancement of this technology, we are seeing many benefits in the coming future. For example, we are looking forward to improved safety, to have to better economic and social benefits, and also better mobility capabilities. Now, unfortunately, there are some shortcomings happening, and we still are limited to the LiDAR and radar sensor capabilities. Better conditions can hugely impact the quality of self-driving vehicles. Traffic conditions and congested areas are also a struggle for autonomous vehicles. And the difference between traffic laws and regulation in different locations can cause problems for self-driving cars. But the hope is that as this car drive more and more mileages are added in terms of data to their databases, it can help to improve the quality and performance of these self-driving cars. Now, in terms of car following behavior, if you look at the literature, you can see that car following behavior is of interest to many transportation researchers because it can promise a better flow throughput control, it can improve the on-road safety, and it can improve the energy consumption. So, and many more things, and all of these things are very promising for transportation researchers. If you are looking into car following behavior, you can see that there are two main categories. The first one studies the stability of the traffic flow. It can be in terms of string stability or plant stability. And the second category, which is of our interest for this work, quantifies the car following behavior using a statistical tool, which can be as simple as the analysis of mean or variance. Having a deeper look at the car following behavior in the literature, you can see many examples. For example, Liu et al. Provided a two-way ANOVA and showed that the different speed limits can have a significant influence on the time headway of the drivers. And please have in mind that time headway usually is the go-to criteria or metric when you are modeling the car following behavior of the drivers. Another example was the factorial ANOVA analysis conducted by Jill Cream, which determined the interaction between area type, number of lanes, and vehicle type can influence the car following behavior of the drivers. Also, Wang and Huchin studies showed that the road condition is a critical factor in influencing the car following behavior of the drivers. And many more studies are out there to show or study the different factors such as a vehicle type impacting the car following behaviors of the drivers. Now, in this talk today, we are interested to answer this question. Is the car following behavior of human drivers affected when following autonomous vehicles? To address this, we provided or proposed this framework, which has two main phases. The phase one focuses on data acquisition, and the second phase focuses on analytics in order to answer this question. Before moving forward, I need to mention that, as shown in the previous works in the literature, we relied on time headway to model the car following behavior of the drivers. And time headway is defined as the time it takes for the following vehicle to reach its leading vehicle. Now, before moving forward, let's focus on the two data sets that we are introducing in the data acquisition phase, the LIFT L5 or LIFT Level 5 and NGSIM or Next Generation Simulation dataset. The LIFT L5 contains raw camera, LiDAR, and radar data. It is collected from a fleet of 23 autonomous vehicles, fixed high-demand routes in California, vehicle positioning based on a global coordinate system, velocity, and unique ID for each agent is provided within this data set. And on the other hand, NGSIM includes detailed vehicle trajectory data in 4 sites in California and Georgia, contains vehicle ID global coordinates of the vehicles, vehicle type, velocity, acceleration, space headway, and time headway. And what we extracted from these two data sets is the time headway series for each legacy vehicle in a situation where the legacy is whether following an autonomous vehicle or a legacy or another legacy, basically. Now, going back to the first phase of our proposed framework, one other item that we needed to address is that how we can make sure that the legacy or the regular car can, have seen the leading autonomous vehicle or not. For that, we applied a change point analysis in order to identify at which time exactly the driver of the legacy has observed and understood that he or she is following an autonomous vehicle. But at this point, we are done with gathering our data, and now we are ready to perform our analytics in order to answer the question of interest. Now, we are going to be going through a couple of steps just in order to prepare the data that we gathered, and then we are going to be fitting a statistical model in order to answer the question of interest. The first step for preparing the data is stationarizing. Now we are working with time headway time series type of data, and a lot of time when working with time series, autocorrelation can cause many problems. So at the first step, we are going to be stationarizing the data and take care of autocorrelation using partial autocorrelation functions and lag differencing. Once the time series are stationarized, we are going to apply balancing through random sampling without replacement in order to make sure that we have a balanced data set, because when we are fitting a statistical model, having a balanced data set helps to maximize the power of the test or the model that we are fitting. Once we have a balanced stationarized data set, we fit our model of interest, which here is a nested factorial design model. And once the model is fitted and we have the result, we can follow up with pairwise comparison using least square means. And finally, we will check the adequacy of the model in order to make sure that the assumptions we made while fitting the model are all holding true. In terms of autocorrelation analysis, you can over here you can see 3 different plots of 3 different samples of data from the LIFT data set. And as you can see, for these samples, we are showing the autocorrelation lags using autocorrelation function or partial autocorrelation function in red. The difference between autocorrelation and partial autocorrelation is that because partial autocorrelation isolates the autocorrelation to a specific lags, it is easier to see which lag is giving us autocorrelation technically. So as you can see, each data point at time is highly autocorrelated with itself, which is not a problem. This is something that we completely understand, but we don't want to see any autocorrelation with the incoming lags, the second, the third, the fourth, and so on. So what we observed after applying partial autocorrelation is that the dataset within LIFT or NGSIM datasets, both of them were highly correlated within the first lag. And after doing the first order differencing, we took care of the autocorrelation, and we had a stationarized data set where the autocorrelation wasn't a problem anymore. There was no significant autocorrelation happening anymore. After that, we perform some balancing in order to make sure that the data set is balanced to fit this model. This is a nested factorial model that we are fitting here. Y is representing our car following behavior, which is modeled as the time headway, and it is the function of mu, which is the overall mean, plus some other factors that we are counting in. These factors are the Platon structure, whether again whether we have a legacy following a legacy or a legacy following an autonomous vehicle, the road type, whether we are in a freeway or an urban area, the time period, whether we are getting the data in the morning or afternoon, and the lane of choice, whether we are in the right, middle, or left lane. Now, looking at the structure of the data provided here, you can see that the lane and road type are impacted on the platooning structure. So, for example, if we are looking at the legacy following autonomous vehicle, we can see that we are somehow limited only to urban area, and we are limited to only the right lane. And as a result, because these nesting structures are happening within our data set, we chose to use a nested factorial model as well. Now, you can see that we have the car following behavior is also a function of alpha, beta, gamma, lambda, and theta, which capture the effects of time period, platooning structure, data source, road type, and lane, respectively. The parenthetical subscriptions illustrate the nesting structure of the model, where the alpha time beta within parentheses is helping us to also study the intersection between the time period and platooning structure of the model. The remaining symbol over here, we have the epsilon, which represents the error within our observations. And the main assumption here is that this error would follow a normal distribution with mean 0 and a constant variance of sigma square. Now, although by its own, we are done with modeling the behavior of the car following behavior of the driver as a function of these different factors, the problem is that because this nested factorial model is not identifiable, we need to add this additional set of constraints in order to narrow down the solution space to a unique set of fitted parameters. Now, once we add this set of constraints and we fit the model, we are going to be dealing with a single nested factorial model that can help us to answer a few hypothesis tests regarding whether any of these factors can significantly impact the behavior of the car following model of the driver or not. Once we fit the model, the first thing that we need to check is the adequacy of the model. And as you can see here, we are showing visually that the normality assumption and the constant variance assumptions are met. We also run some tests to double check whether these assumptions are true, and all the tests confirm the same, fact that the assumptions are met. Now, looking at the result of the nested factorial model, we can see that the only factor that was significant was the platoon structure, which means that whether the legacy is following an autonomous or another legacy vehicle is significantly impacting the car following behavior of the driver. Now, other factors that we studied was a time period, which seems to be not significant. We also studied the interaction between platooning structure and time, which seems to be non-significant. We also studied the nested structure of the data source, row type, and lane based on the platooning structure that we had. Again, legacy following legacy or legacy following autonomous vehicle, and none of them seems to be significant in our ANOVA model. Now, we followed this the result of ANOVA with pairwise comparison using least square means. And as you can see here, although there are some significance observed when we are comparing the time period and platooning structure and lane and platooning structure, the main significance is coming from the platooning structure, as we discussed in the first table. So in conclusion, we can say that in this study, we proposed a nested factorial model to study the potential effect of autonomous vehicles on a human driver's car following behavior using naturalistic driving data from NGSIM and LIFT L5 prediction datasets. We consider many different factors such as platoon structure, time period, traveling lane, and road type. And among all of these, the platoon structure seems to be the main factor that significantly impacted the car following behavior of the driver. So the result indicates that in real world setting, a human driver's car following behavior actually differs when following a legacy vehicle compared to when following an autonomous vehicle. With that, I'm going to conclude my presentation. And if you have any questions, please feel free to reach out to us at sarahmasood@vain.edu or nmasood@umich.edu. Thank you for your attention, and please enjoy the rest of the conference.